Right, so I was saying, mentioned some recent applications that have broadened up the field and give rise to the motivation for doing this school. So for instance, the famous Bondi energy loss formula, this can be derived from Nether theorem. Consequence. And so this has applications for gravitational waveforms, and more in general for studies of perturbative classical gravity. And in particular, there are various ways in which people study perturbative classical gravity, post-Newtonian approximations, post-Minkowskian approximation. One very powerful way of doing it is the effective field theory approximation and the study of amplitudes. And so this is what will be covered by Carlo Heisenberg in his, what are the lectures called now? Amplitudes something, okay, which will be later in the week. So that's the first topic that we're going to make connection to. There are very important, so I mentioned perturbative classical gravity. There are very important applications to perturbative quantum gravity. In particular, through soft theorems. And this was really spearheaded by Strominger, which like 10, 15 years ago started, or at least contributed a lot to this kind of like blossomed of new interest in these asymptotic symmetries by exposing this connection between the BMS symmetries and soft theorems. So this is really Strominger's infrared triangles. And so these, as then later gave rise to the topic of celestial holography. Now this was supposed to be covered by Sabrina Pasterski, who unfortunately, she sends her apologies, could not make it. Fortunately, we have Tim Adamo that is hiding behind his laptop up there, who is frantically preparing his classes on celestial holography. At least trying to remember what it means, I hope. And so he very kindly agreed to cover up for her. So this is the connection with this. Which order do I want to mention the rest? You will see that the study of these BMS symmetries has a lot to do with the geometry of null hypersurfaces. And there is a very interesting approach to study the geometry of null hypersurfaces from a purely intrinsic viewpoint. And this has the funny name of Carolian geometry, which I will not spoil. Why? Because this is going to be covered in Yannick's class. Now, the geometry of null hypersurfaces and the study of null rays more in general is also what spurred Penrose and also Newman to study and introduce and study twistors, which is a beautiful mathematical tool that has a large number of connections by itself. It's used in integrability, it's used in classical gravity, it's used in amplitudes. And we have the pleasure of having an academic son of Newman to teach us about this topic. And that will be again Tim. And this was the original class he was supposed to give. Okay, so that's just to give you an idea of how with Dario, Andrea, Sabrina, and Laurent, we thought about this workshop. That is an idea of bringing together researchers from all the world that are interested in these different topics and bringing them together to interact among one another. And we are very excited to say that the response to it was really excellent. A large number of people are coming in the next few weeks. And the high point of the activity will be on the 4th week, when we will have the conference in which more or less all the participants will be there. So I hope you as younger students will be also interested in, maybe you work on one of these fields, maybe you are entirely new, but I hope that you will appreciate not just one of them, but also how they are interconnected, and how progress in the field can come from bringing together different ideas. So that was for like the overview of this, what these classes will be about. And for the overview of my class on asymptotic symmetry, then what I will like to present are covariant phase space and Nether theorem. Asymptotic BMS symmetries in gravity, and extensions that have been more recently discussed, and the construction of charges and fluxes. So that's how I roughly plan to divide these into 3 classes. Of course, today I'll hope I'll be able to go through all of that. So let me maybe start right away, unless there are questions about the general organization or the workshop or of the school. Don't hesitate if you have questions to contact me. If there are local questions, you can also take advantage of the staff here. But otherwise, please ask me for any questions you have. Okay. So what I would like to start is by telling you a little bit about what the covariant phase space is and why it's so useful. I'm assuming that you have hopefully some background in the usual construction of the phase space, which is by Hamiltonian methods or canonical methods. So usually we associate a phase space structure to initial data. So what we do is that, let's say we have trajectories in time, and then we chop these trajectories by giving some initial time slice, and then at each point along the trajectory, we read the position at that time. So let me call this just Q0, let's say, and the initial velocity or momentum at that time. And these, let me remove these zeros, and then we associate a symplectic structure by giving a symplectic form. I usually take conventions dp dq. If you're used to the conventions dq dp, anyway, it doesn't matter so much. Minus signs will be involved. Don't assume that all my minus signs will be right or numerical factors, but I have been putting together notes in which hopefully those will be right. I would lie if I say that I didn't hope to have them finished before today. It didn't happen. I'll try my best to make them available by tonight or tomorrow morning so that you can have them for tomorrow's classes. So this is how we usually think of phase spaces. We have a differentiable manifold that is given in this case by the cotangent bundle of R, and we equip it with the symplectic 2 form, which has the property that is closed. That means the omega is 0. It's non-degenerate. That means that on every vector field, it gives a non-zero result. If you want, it means that there is an empty kernel to the symplectic 2 form. There are no zero modes, namely there are no vector fields with 0 eigenvalue. Okay? So invertible if you want. And the fact that it's invertible means that it gives access to Poisson brackets as well. And then you can prove that easily that this is conserved in time. dt of omega is equal to 0 on shell. And this happens because dt is a Hamiltonian vector field whose Hamiltonian is the Hamiltonian, right? I'm assuming, are you familiar with the notion of Hamiltonian vector fields? Maybe not, yes? In Fourier space, you said? Space-time, yes. No, no, not yet. I'm talking, oh, so this is defined on this T star of R, this cotangent bundle. So the vector fields, so the generic vector fields, V, will be things like coordinate Q dq plus coordinate P dp, okay? So we're gonna build on these R, let's say that this was trivial topology, so let's say this was R cross R, so R2. We're gonna build now a tangent bundle and a cotangent bundle on this R2, and that's where we're going to define our differential calculus and exterior derivatives, okay? And so now one form, let's say alpha also would be alpha Q dq plus alpha P dp. And what does it mean to be an Hamiltonian vector field? So an Hamiltonian vector field has the property, by definition, that the Lie derivative on omega is 0. That's the definition. And this definition has a very important consequence. So we use Cartan's formula for the Lie derivative. So this is IV d omega plus d IV omega. But by definition, our omega is closed. So this term is not there. And therefore, we see that IV of omega, we see that the Lie derivative, yes, this remains this. Now the definition I mentioned is that this is 0 because it's conserved. So this is to be equal to 0. Okay? So that maybe I should have written it here. Definition of Hamiltonian vector field is that Lie derivative with respect to V of omega is 0. Then I use Cartan's formula. This term vanishes because it's closed by definition. Therefore, we are left only with this term. And if the vector field is Hamiltonian, this has to be 0, which means that IV of omega, if I assume that the cohomology is trivial, is exact. Okay? And the potential, I'm going to call it H, for the Hamiltonian of the vector field V. Now, this nomenclature comes from the fact that if the vector field is dt, it is an Hamiltonian vector field, and the Hamiltonian of dt is actually the energy, so Hamilton's function. Mathematicians, on the other hand, they call this the moment map, because if you think of these as, oh, sorry, yes?
You said that you were assuming a trivial
cohomology. Cohomology, yes, yes, yes. Because you see, otherwise, namely, I'm saying that if it is closed, it's exact.
Yeah. But are we gonna work like outside this assumption?
We will not need to, because we will have already enough trouble when we switch this to. But the issue of a non-trivial cohomology is not very important, fortunately, because there's a beautiful theorem by Wald that proves that for classical field theories, you can work with, well, maybe I'll get into that later. Let me not get too sidetracked. But no, for, I think all of what I will say, we will always assume a trivial cohomology.
Excuse me. Are you assuming that you have gauge symmetries?
No, not yet. I'm still, not yet. Because you see, I'm not there yet. I'm assuming that it's non-degenerate.
Because the initial conditions when you have gauge symmetries that are not in number the same.
Exactly. So I'm not there yet.
Not
I hope I'll get there. Okay, no, right, okay. Okay, so these mathematicians call it moment map, because another example of this is the momentum as the canonical generator of translations, okay? Okay, good. So these are the properties that we have in standard no-gauge symmetries, just point particle, simplest possible system. This is the canonical construction of the phase space. You see, it relies on a choice of time. So now when you apply these same ideas to field theory, even without gauge symmetries, you will see that this formulation is, in a sense, very non-covariant because it forces you to choose a space-like hypersurface to begin with. And now, in special relativity, you can get away with the fact that you can always choose a simultaneity surface for some inertial observer, and then you know that all the others are related by Poincare symmetries. So you're breaking covariance by choosing one, but in a way that is mild, it's easy to keep under control through Poincare transformations. But in GR, there are no simultaneity hypersurfaces. Any choice of space-like hypersurface you will do in order to formulate the theory in the canonical system, which is so-called the ADM formulation, for those of you that know it already, will be strongly non-covariant, and recovering covariance is usually quite painful. And so it's very convenient to have, on the other hand, an approach that doesn't do this. And so the beauty of the covariant phase space is that it gives you a symplectic structure without choosing time, therefore without choosing a definition of momenta, because remember that these momenta are P is dl over dq dot. So if you don't define first an hypersurface and what you mean by time, you don't even know what momenta means. Okay, so this whole construction, then you do the Legendre transform. So this whole construction is very non-covariant in the sense that it relies on one choice of time. And what's the idea? The brilliant idea is to associate a phase space structure not to the initial data, but to the trajectories themselves. And actually, this idea dates back to Lagrange himself. So even before the phase space was formulated in precise mathematical terms by Hamilton and the colleagues of the time, Lagrange already had this idea. And so how do we do that? Well, instead of thinking of R2 in this example, we actually think of the functional space Q of t. So let's call this the field space. So these trajectories, and these in the one-dimensional case would be just Q of t, but these can easily be generalized to field theory, namely, if we have a scalar field, let's say for simplicity, x mu, I mean time and space, for instance, okay? So let's use this notation. Mu will be 0, 1, 2, 3, and A will be 1, 2, 3, to distinguish between space-time and space if I choose a foliation. So in this case, this would be my field space. So if you want, you can think of these as a field theory in 0 spatial dimensions, and this is a field theory in 3 spatial dimensions. So the idea is to give a symplectic structure to this space of functions. And how do we do that? Well, first of all, how do we even give now? There was the question, what is the differential structure? So how do we think now of these as how are we going to build the vectors and differential forms on this space? We do it using a mathematical construction that is called the jet bundle. But you don't have to, like the mathematical structure we had here was the tangent bundle. But you don't have to go into the mathematical details too much. Just always think about the fact that we are, like, in a physics sense, we are thinking of a space in which the number of degrees of freedom has now become infinite. So instead of having, if you want, one variable, we have one field worth of variables. You can think of this t, if you want, as a continuous label. So suppose that instead of going all the way from 1 to infinity, let's do an intermediate step. Instead of having one particle, let's say that I have n particles. So I would label them with an index I, right? Where I goes from 1 to n, the number of particles I have. And now imagine that this index I becomes continuous. Okay, so imagine now that I, instead of being, I don't know, in the natural, or have an infinite number of particles, I actually make it continuous. And instead of calling it I call it T. Okay, so that's kind of like the way in which you can simplify in your head this mathematical construction and get intuition around it. These are just vectors whose label, whose number of components is infinite, and whose label that tells you the component, the entries of the vectors is this continuous label T. Okay, let's take it in those terms. So then the next mathematical ingredient that is going to be very useful is that we can take now the differential of this function. So this is the differential. Now usually, if you've done a little bit of functional calculus, you would think of this as a variation. But what is very convenient is to think of this really as a differential as in a one form. Namely, maybe we can make a useful analogy. So if you want, I have in the usual exterior calculus, I will have coordinates, x mu, and I will build their differentials. Then I would have, vectors like those. They would be vector fields, sorry. They would be like this. Then I have forms. That would be like this. And then I can construct a whole layer of operators, such as the internal product, the exterior derivative, the wedge product between forms, and the Lie derivative. Right? Standard Cartan calculus or exterior calculus, I don't know, infinite dimensional space. Then we're going to build exactly the same objects, but on this infinite dimensional space. So instead of having x mu, we're going to have phi of x mu. Okay, so mu has now been, okay, let's maybe for simplicity, let's say phi of t. So mu has become t, and x are the field components, right? So let's say this was q, to avoid the, okay, so x has become q, mu has become t. So these are now these differentials. Vector fields would be functional derivatives. So a vector field would be something like integral over dt of some functional of q of t, functional derivative. Forms will be generic integrals over t of some functional contracted with this. We can define inner product, so forms will be integral of some functional, I don't know, let's use another, okay, let's call this v. And this f of q of t delta qt. When we do then when we get this formula, we use d mu x over d, dx mu over dx nu is a Kronecker delta. At the functional level, we're going to use this identity. Right? And so the equivalent of this inner product, to distinguish it now from this finite dimensional case, I'm going to use capital E. So this will now, you get two integrals, one Dirac delta, so that gives you back just one integral, and it's the convolution of these. So you see, hopefully, this analogy should be easy to understand, and this is a number, because I'm taking a functional, another functional, I evaluate it on a specific solution, let's say, and then I integrate over time. All these integrals are integrals over time. We can do the wedge product of forms. I'm going to define the symbol for the exterior derivative being delta. And I'm going to define the symbol for the Lie derivative in field space as delta v. So this would be IV delta plus delta IV. The reason why I use this notation and not like some books do, like a capital L, is because you see that if you act on a scalar, like for instance the Lagrangian, this term vanishes, and so you get that the variation of the Lagrangian specified to a specific vector field is its Lie derivative, and so you recover the usual interpretation that we have in books of specializing the variation of the Lagrangian to a specific variation and using the notation delta v for it. So that's why I'm using this notation. Yes? I'm so sorry, I haven't really. For the differentials here? This one, yes? we apply it on scalars, for instance. Oh, yeah, that's, yes, of course, yes. Okay, excellent question. So, if there is only so you see in this example, I have only one continuous label. So it's like if mu is only 1, takes only value mu equal 1. And that's why we have a single integral. Now, if I create another layer here, so we could do the other case. Okay, let me do it here, this one. So that so now we have phi of x mu now. So we have delta, phi, this is the differential. And now when we come to the vector field, we do exactly as you say. The vector field will be the integral over d for x. All of them, absolutely. No, thank you for the question. Yes, absolutely. So, okay. So even though the physical differences in going from 0 spatial dimensions to 3 spatial dimensions are huge, and we're going to discuss many of them, one of the power of this language is that the transition goes really smoothly. This integral over dt is like we had just one component here. Now we have 4 integrals, which is like we had 4 components here. Okay, so this is part of the reason why it's so convenient. Okay, so keep this kind of like dictionary in mind in order to go from one to the other. Now, how do we add now a symplectic structure? And so the idea to add a symplectic structure, okay, this I think I've covered. No, one thing to say. So because of these 2 layers, you see that we have equipped, so not yet the symplectic structure, but already at the differentiable level, we have equipped our space of fields with 2 different notions of exterior calculus. We can do derivations on the base manifold. We can do derivations in the field space itself. Okay? So the fact that we can do both, this means, and we can do cohomology in both cases, this comes with the name of variational bicomplex. Now, to prove that this is consistently a unique system with 2 different directions, which you can think of as horizontal and vertical, for instance, one needs to define a total differential and shows that it squares to 1. And now, typically what people do is that they define the total differential as d plus delta. So this would be the total. And then, in order for it to square to 0, you're going to assume that d and delta anti-commute. Okay? Because you see, you're going to get d delta plus delta d, and you want that to be 0 in order for this to be a total differential. Now, I don't like that because it gives a awful lot of minus signs, which I always fail to keep track of. So the alternative is to define the total differential. So alternative is to define the total differential in a graded way. So we're going to define it as d minus 1 plus p, where this is the p-form degree in space-time, this is the p-form degree in field space. So this is my total differential, and now I get, I don't know what to call it, let's call it delta, and now I get that delta squares equals 0 with commuting quantities, okay, which simplifies my life a lot. But if you look at reviews of these, for instance, the book by Anderson or Barnich, you will see that typically it is defined in this convention. Don't be worried. Some signs along the way will be different, but there's not much subtleties into it. It's just a different convention. Okay, so this is another name that opens the way to a lot of fancy mathematics, like the jet bundle. We won't need it much. So don't be, yes. Yes. For this, you will have to tweak that with this grading for this to work. Absolutely, yes. Yes. Yes, of course. Yes, right. Yes.
Data is used. Is that is rate used from vector fields on G1?
Yes. And it's only and only ever in this space of sections that I will be working. So if you want, from the practical viewpoint, what we need this structure for is the fact that it allows us to think of this guy and this guy as independent, because these are different jets. So we're going to think of this. So, okay, so these two different jets. They will not be independent once I evaluate them on a specific trajectory, but as abstract jets, I'll take them as independent, which means that, let me use a notation like this for wedge product in field space, which means the quantities like delta Q wedge product in field space, delta Q dot, are non-zero, okay? Never zero. Notice also that delta Q T wedge delta Q T prime is also not zero unless T is equal to T prime, because this is like dx mu wedge dx nu. This will be zero, when mu is equal to nu, but not otherwise. So similar in this construction here. So maybe it looks like a lot of abstract stuff, but you will see that it becomes very powerful and very convenient, because, for instance, this construction of the phase space and derivation of Nether theorem, you will see how simple the formulas are, how elegant the proofs are, so it will pay off. I actually also resisted it myself, I should say, for a while, because most of the original papers on the subject, so all the papers by Wald, for instance, they only use the standard language of thinking of delta Q as a functional variation. And admittedly, a lot of kudos go to Daniel Harlow in his paper with Wu, where they actually pushed. They didn't have the idea of using the variation by complex, of course. This dates to back to the even 70s with work by some Polish school, but then it was reprised by Ashtek and Streubel, even by Witten. But they really, Harlow really pushed for its use in simplifying a lot of the formalism, and he gave a very important other idea, which I will come to soon. Okay, so having all this mathematical structure at disposal, now how do we construct the symplectic form without going through choosing time, but only speaking about the trajectories? What we do is that we look at the Lagrangian, and for notational purposes, it will be convenient to think of the Lagrangian not as a scalar, but as a top form. So L Lagrangian as a top form. So I will write it as, let's say, curly L, this will be my scalar, times epsilon. This is the volume form. So if you are in flat space-time, this will be just d for x. If you are in curved space-time, on the other hand, this will have the volume element in it, okay? So for instance, for a scalar field, L would be d mu phi minus v. And for gravity, this would be r minus 2 lambda. And the square root of g goes in there. Okay? Sometimes, maybe I will also use the notation L twiddle to put back in that numeric, factor, so that this is now not a scalar, but like a density. Okay, twiddle for the density. Okay, so I'm going to think of it as a form for simplicity of some formulas you will see. And then when we compute the variation of the Lagrangian, we're going to get the equations of motions. Let me just call them E, like for equations of motion. And then typically, we get also a boundary term. So if I'm thinking of this as a form, the boundary term would be an exact form, so theta would be a 3 form. And if I, on the other hand, think of this as a scalar, then I would write something like, I don't know, field equations, let's say like this, plus in flat space-time, let's say something like this. Okay, so typically we get this, we're going to see examples. Actually, no, let's see an example. Let's take this example here. So my Lagrangian in that case would be 1/2 m q dot squared minus some potential. And because I want to think of it as a top form, I'm going to write it like this. Okay, this is my Lagrangian. So when I do the L, now I'm going to get m q dot delta q dot minus the contribution from the potential. Now let's look at this term. This is delta q dot. So this is delta d over dt q. With my conventions for commutation, this is like a d. So from these rules, it also follows the delta d mu on a scalar commutes. So this commutes, so I can write this as d over dt delta q, and then I can integrate this term by parts, and so I get d over dt m q dot delta q dt minus, you will see when I integrate by parts, I get m q double dot, so I get m q double dot dv delta q dt. So these are the equations of motion, E, and this is my boundary term. I can remove these two. So from this equation, we read that theta is equal to m q dot delta q. And now you can see that we are kind of like on the right track to construct a symplectic structure, because you see, these, if I now choose time, a time slice, so now these trajectories are no longer functions, they are evaluated at one specific point. So I could think of this as my dq. Then I can recognize this as my p. So you see that if I do that projection, then this guy becomes p dq, which is my standard phase space. Symplectic, this is called the symplectic potential, and then the d of this is the symplectic 2 form. So maybe I should have added this here. Because it's closed, locally at least we can always find a symplectic potential for it, and we said we're not going to go too much into cohomology, so let's assume that I can do it even globally. I don't have to, but that's a good point. So you can distinguish, between equalities that will be valid off shell and equalities that will be valid on shell. This distinction is very important. And we are able to, as you can see, I don't have to go on shell in order to define the symplectic potential. But many of the equalities that I will derive, many of the properties will need that. But it's important to keep in mind that you have these different layers. You have a field space, abstract space of trajectories, not necessarily solutions, which you can already equip with a lot of mathematical structure. And then you can see what happens to the mathematical structure when you go on shell. I will use because this distinction is important, I will use the notation equal with a hat. That will mean on-shell equality. Okay, so we're going to see this appearing soon. Okay, so this was just to motivate that we are on the right track, and also the importance of that comment there, because you see that then omega delta theta, so this the exterior derivative in field space, not in space-time, so that's why I'm using this delta now, is going to be m delta q dot, curly wedge, delta q, okay? Okay, let's see a few examples to make this a little bit more concrete, and introduce also the notion of gauge symmetries as the general directions of the symplectic form. So maybe the simplest next example to do is the scalar field. So you see, the scalar field is really, really the same calculation, okay? I do delta either here or there is the same thing. So that takes rid of this factor of 2. And then I have a d mu, or let's say it's up, d mu delta phi. I have this term, which again I integrate by parts. So I write it as, sorry, which first I use the commutator rule to write it like this. What am I doing? No, it's the other way around. Okay, let me do it, and then we see. Okay, so delta L would be minus d mu phi, d mu delta here, but because they commute, I can write it like this, and then minus d phi v, delta phi, just as a scalar. If you want, we can do the calculation like this. So now I integrate here by parts, and so I'm going to write this as minus d mu phi. I want to write it the other way around. D mu delta phi, d mu phi. I want to write it like that, so that when I integrate by parts, I get minus d mu phi delta phi plus box phi minus d phi v delta phi. Okay. These are my equations of motion, and so theta mu is minus d mu phi delta phi. We can again check that we're getting something meaningful, because if we project, if we choose t equals 0 initial slice, then the pullback of the 3 form corresponds to the time component of this vector. And so this is minus d0 phi, which is phi dot. And this we recognize as pi, the conjugate momentum. So we see that we are reconstructing the standard symplectic structure also from the canonical viewpoint. Okay? So this is like a sanity check, if you want. So that's a symplectic potential. And maybe from a comment about this bicomplex viewpoint and this grading that we briefly mentioned, it's useful to explicitly give at least once the grading of these various objects. You will see that L as a functional is a scalar in field space, but it's a top form in space-time. So this would be like, let's say, a 4 form and a scalar in field space. So space-time, field space. So little p is 4, big P is 0. But how about delta L? See, delta L now is a variation, which we said we're going to think of it as a differential form. So this is a 1 form in field space, and so delta L is still a 4 form in space-time. I haven't touched anything there yet, but this is a 1 form now in field space. How about theta? Theta depends linearly on the variation, so it's still a 1 form in field space. So this is still a 1 form. On the other hand, we have removed 1 form grading with this D, so it's a 3 form. And how about omega? Omega is the delta of theta, so it doesn't change the fact that it's a 3 form. But on the other hand, it increases its grading by 1, so it's a 2 form in field space. Precisely like, no, it went away, but so when we said in the standard canonical approach that omega is a 2 form, was a 2 form on this cotangent bundle of the cotangent bundle, now it's a 2 form in field space. Now, one difference, important difference between mechanics and field theory, because of the extra spatial dimensions that come in, is that in the mechanical case, this is already the symplectic potential, and this is already the symplectic 2 form. But in the field theory case, these are not. These are just giving you the local degrees of freedom of 1 point. But if you think about a field theory, you have infinitely many degrees of freedom, 1 per point. So these, in the field theory case, are actually, we call them symplectic potential current because the actual symplectic potential would be, let me call it capital theta. This is notation from Wald. So we will choose some, maybe I don't need to do, we will choose some Cauchy slice that contains all the data in order to predict the evolution of the theory. And then the integral of the current on this Cauchy slice would be the actual symplectic potential. And similarly, for the two form, we will call this the symplectic two form, in this sense, two form current. So a three form because we are in four space-time dimensions. And capital omega, the integral over sigma of omega, this is the actual symplectic form. Okay? If there are no spatial dimensions, you don't need to do these integrals. You already have your phase space. But you see, this already should make your brain stick a little bit that in order to talk about phase space in field theory is not enough to just give you the symplectic form. I have to give you also the sigma. And now there's various things that we're going to discuss about how we choose the sigma and what conditions are needed. Because one important, and then I'll go back to these examples. Because one important, so with the scalar field already we have one example in mind of that, because the sigma, so could be infinitely extended, and phi goes to 0 asymptotically. For instance, in quantum field theory, this is what we often assume. Space Cauchy slice infinitely extended, fields go to 0 at infinity, we can invert the covariance, we get the propagator, right? This is typically how we use quantum field theory, how we start quantum field theory. This omega, remember that is conserved in time in the finite dimensional case. You remember I'd shown that omega dot on shell is 0 because this is generated by the Hamiltonian, so you can easily prove that on shell this is the D, this is a double D of the Hamiltonian, and so it's 0. In the field theory case, you don't get an equation like this. The equation you get in the field theory case is d omega. So remember now, we have that omega is closed, so delta omega is automatically 0. That's the equivalent of the statement here that d omega was 0. But here now, the new statement that we have corresponding to that is that d of omega is 0. And to prove this statement, you can look at this equation here, and you can take the double variation, so that will give you a 0 on the left-hand side. It will give you a delta of the equations of motion, and because of our commutation rules, it will give you the d of omega, right? So you see, if I take, so I have 0 equal double L, double, whatever it is, equal delta L plus d omega. So that means that on shell of the field equations, not only for the background, but for whatever perturbations you're considering in this variation, then d omega is 0. And therefore, we get our equation. Now, does that mean conservation in time? Not immediately, because if I now use Stokes' theorem, so let's treat a more general case of which this is a limiting case. So let's suppose that we have like a time-like cylinder with some initial slice sigma, some final slice sigma prime, and some time-like boundary t. Now I apply Stokes' theorem, and I get, from that equation, I get that omega, using that notation, capital omega is the integrated one. So omega on sigma is on shell equal to omega sigma prime plus omega t. This is a very important equation for us because it shows that as long as you can neglect this lateral symplectic flux, so let me call this, I don't know if it's an orthodox name, but let's say lateral symplectic flux, then omega sigma is equal to omega sigma prime. The phase space structure is conserved in time. Okay? All the information about the data here is enough to reconstruct the solution everywhere, and same for there. So you can clearly see when these go wrong. If you have, for instance, radiation can go outside. For instance, in the case of the scalar field theory, it has radiative solutions. I give data here. Radiation can go outside. Radiation can come in. And it's fairly obvious, intuitively, that giving the data here is not enough to reconstruct the solution everywhere. What you need is also the contribution from the side. So it's tricky to determine what your phase space is. So from the point of view of the covariant phase space, you can just say the phase space is associated to all of the solutions. But now if you want to map this to a notion of data, free data, you have to be a little bit more careful about what your hypersurface is. Now, that case is when we take this time-like boundary all the way to infinity, the fields go to 0 appropriately, so that this guy vanishes. And then we know that all the data here are enough to reconstruct the solution. And we know that the symplectic form is constant. That's a standard situation. But in dissipative systems, when we want to study radiation, the behavior of radiation, it's more interesting to keep track of the radiation. Now, keeping track of the radiation using a time-like boundary is really complicated. It's complicated, first of all, because radiation can be outgoing or can be incoming. But it's also in gravity, it's also more complicated because on a time-like boundary, just on a space-like boundary, you don't know what the physical degrees of freedom of the theory are. Because the physical degrees of freedom of the theory are the solutions of the Hamiltonian constraint that is nonlinear, and the exact solution is not known. But we can fix both problems at once if we change this lateral boundary to a null boundary. Now, if we choose a null boundary, we have to decide whether if it's incoming or outgoing. Let's say it's incoming, then things will look like this. This is my sigma, this is sigma prime, and let me call it n for null, this is T for time-like. Now, this is the incoming case. The outgoing case would be this. By incoming or outgoing, I mean this null rays. By causality, and the fact that nothing travels faster than the speed of light, even though, not very far from here, a few years ago at the Gran Sasso experiment, this was, for a moment, a very exciting change in our perspective. Then it turned out to be just, lots of wire being wrapped up and forgotten about it. So by that assumption that causality holds, no radiation can come here. So by choosing these boundary conditions, I'm describing only outgoing radiation. By choosing these boundary conditions, I'm describing only incoming radiation. So already it sorts out nicely whether I'm doing dissipation or whether I'm doing absorption. And not both at once, that then will have to be taken into account with additional boundary conditions. That's already taken care of. But more importantly, on null hypersurfaces, the constrained free data of full nonlinear GR are explicitly known. And this actually is not a new result. It's a result from 62 by Sachs with follow-up work. Randall or Rendell, I can never remember. In the 90s, sorry? With E, thank you. And crucial, also in the 90s. So this result has been refined, extended, mathematically solidified, lots of cool developments on it. But the gist of the result is the old one, that if you give the shear, and we will briefly mention what the shear is, the shear of this hypersurface is a constraint free data for the evolution. The downside of this approach is that you cannot reconstruct spacetime everywhere, because typically, if the hypersurface is null hypersurface has shear, so it's non-trivial, then it also develops caustics, so its coordinate description is typically truncated to a very small domain, and so you can only do reconstruction in a very small domain, then you have to set up a new coordinate system, do it again, so it's not very practical. But it's conceptually, it's very useful, and this issue of caustics, for reasons that we will see tomorrow, goes away when you are infinitely far away from a modeled, when you are modeling an isolated system. so in the description of free journal infinity, and therefore you have an identification of constraint-free data that is global there. So that's why it's a little bit more careful, the issue of boundary conditions, the issue of conservation in time in a field theory, and it makes it very important to talk about the boundary conditions that one has at these lateral or these null boundaries. They could be conservative, no radiation incoming, no radiation outgoing. They could be leaky. And this changes the picture completely for both the conservation of the symplectic two-form, but also the application of Nether theorem. Okay, so with that in mind, let's see now the first example of a gauge symmetry. This would be, let's say, Maxwell.
Is there some connection with the Donder-Deville multi-momenta?
No. So in that approach, maybe you will talk about that approach. So in that approach, you try to gain covariance in another way by defining momenta, not with respect to one choice of time, but to any Cartesian components, right? So I guess that hopefully most results come up the same, but I'm not an expert on that. So you can ask Janahur about it. In this formalism, you don't use that. You don't introduce momenta at all. You see, you only think of trajectories as your fundamental variations and derivatives of the trajectories as your jets. And the symplectic potential is associated, you see, to this jet bundle. No, I've raised it, but you see, this was T mu was minus D mu phi. In the multisymplectic formalism, you would say, okay, now I have momenta, which are dl over d mu phi, without having to pick a specific mu. But I'm still defining momenta. Here I don't have to, but you can think of this as momenta if you want and make connection with that language. So, yes? Yes. Yes, lots. Maybe I can talk about that now. I was thinking about talking about first the degenerate direction, but we can talk about this now if you want. It goes, yeah, it goes in the same. Yeah, okay, let's do that then. So, conservative and leaky. So let's see some examples. So first of all, to be pedagogical and build up the discussion, I should probably first say that this symplectic structure that we associated to the covariant phase space is not unique. So let me first talk about or ambiguities. You will see why I'm bringing this up. Ambiguities in the symplectic structure. There are two ambiguities. So the first is that delta L on shell is d theta, so this only defines theta up to adding, equivalence class up to adding some exact form. So there's always the freedom of adding an exact form like this. And the second freedom is that the Lagrangian itself does not define a unique set of equations. Sorry, there's not a unique Lagrangian for every set of field equations. The Lagrangian itself is defined by an equivalence class of Lagrangians up to boundary terms. And this changes the symplectic potential by adding a term like this. Okay, so we have exact forms in space-time and exact forms in field space. So the total freedom is that theta can be replaced by any theta prime that is given by the original theta plus a total delta plus a total d. Notice that when you do this, omega is being replaced by omega plus a corner term. Okay, this term gives no contribution. So that also means that if you're getting your alpha here from adding a corner term to the Lagrangian, to the boundary Lagrangian, sorry, that will not affect the symplectic 2 form. So changing L, boundary Lagrangian, to L prime L plus a corner term will not change omega. So this one it's easy to understand how we can engineer it, because for instance, it's easy to think of boundary terms than someone would like to add because of the variational principle, and this is precisely related to the issue of boundary conditions. So let me talk about that first, and then we talk about this alpha ambiguity. So if you look at the boundary conditions, let's say, for instance, for the scalar field, we have seen that theta mu has this form. So you will think of these as, and so if you're interested now in doing the variational principle, you want to recover not just that the equations of motions are satisfied, you would like to recover, so from the point of view of variational principle, you would like the delta L is all 0 on shell, not just up to a boundary term. So you would like that also this term vanishes from the point of view of the variational principle. So how are you going to do that? You're going to do that by imposing the equations of motion and suitable boundary conditions. So if I give you the Lagrangian for the scalar field in this canonical form, so L was minus 1/2 d mu phi, then this Lagrangian is associated with a variational principle which is in Dirichlet boundary conditions. Namely, the field, the fundamental variable, is being held constant in order for the variational principle to be well defined. But I can always switch to a Neumann, for instance, problem. How would I do that? Well, for the Neumann problem, what I would like to do is to have a symplectic potential now that emerges when I do the boundary variation that is of the type phi delta d mu phi. You know, in the finite dimensional case, I would like to go from theta, that is p dq, Dirichlet boundary conditions, to a Neumann, which would be minus q dp, right? So that's what I would like to do. And you can easily check that if you take L given by up to a sign, phi d phi, this boundary term will do exactly the job. So you can switch to Neumann, and now you can also play around with other boundary Lagrangians if you want to study some Robin boundary conditions or whatever you're interested in. The interesting point from the phase space perspective is that changing boundary conditions from Dirichlet to Neumann corresponds to a change of polarization in phase space. Is this a language you're familiar with? Yes, Chris? Yes, but you will have to not use this Lagrangian. You will have to use, so Neumann, you will have to use the Lagrangian L prime, L plus dl, where L is plus or minus that, I don't remember. In GR is the opposite. In GR is the Neumann boundary conditions that gives you a well-defined variational principle. Okay, let me not skip ahead. What was I saying? Dirichlet, these, okay, no, maybe let's talk then about GR, the same distinction in GR. I thought I was wanted to say something else, but. Yes, polarizations. So if you're not familiar, a polarization is a cut of the phase space in which you look at a set of maximally commuting variables, commuting in the sense of Poisson. So basically, if you have Q's and P's, Q by itself is a Lagrangian submanifold, P by itself is a Lagrangian submanifold, Z given by Q plus IP, it's a Lagrangian submanifold because this Poisson commutes with Z bar. And so if you look at sections of the phase space which are described only by Poisson commuting variables, those sections are called, or those subspaces, submanifolds I should say, those are called polarizations. Q is the configuration polarization, P is the momentum polarization, this is called the holomorphic polarization. And you can think of these as physicists as what you need to do in order to write the wave function. You never write the wave function on the phase space, unless you're using coherent states representation, but typically you write the wave function on half of the phase space, you write, and more mathematically precise in speaking, you write the wave function on polarizations of the phase space. So there's this correspondence between boundary conditions and polarizations, which is interesting. No. Lagrangian so a polarization of the phase space is a choice of Lagrangian submanifold. Yes. Yeah. Now, in the GR case, what happens? In the GR case, the situation is more intriguing. Let me do it here. So we do the same calculation. The calculation is slightly more involved, but not much, thanks to an Italian whose name was Palatini. The first proved the identity that this variation, that this is a boundary term. And so you can use this identity in order to immediately derive what the symplectic potential is. Now, because I'm running out of time, I would like to be a little bit fast and tell you that, so when you start from GR, you get a symplectic potential which has, through this identity, so it's not even complicated, you get a symplectic potential that has a structure that is more or less like this. G, I don't remember now exactly the indices, but it's going to be, okay, maybe don't take these indices for real. It's some structure like this. But it's very similar to what happens in a gauge theory. Because in a gauge theory, let's say Young-Mills, the Lagrangian is f squared. So when we do the variation, we're going to get minus f delta f, and, sorry, minus 1/2 f delta f, and we can write this as minus f d, or let's say this is just a scalar, so this was a mu nu, so now I have mu nu, here I have the mu delta a nu, standard identities. Now I integrate by parts, total derivative, delta a nu, plus Maxwell's equations. This is the symplectic potential in the, this is Maxwell. Young-Mills is really the same. Just you have to replace this with the covariant derivatives. So the symplectic potential is minus f mu nu delta nu, and sanity check, you pull back the three-form dual to this vector on t equal constant, you get minus f0, or let's say t0, theta 0, a, because it's antisymmetric, delta a, but this is the electric field. So we get electric field conjugated to a. That's a symplectic structure of any gauge theory, any Young-Mills type or Maxwell type gauge theories. For Chern-Simons is different. So this, and then the symplectic two form is that the electric field is conjugated to the vector potential, which is the standard canonical analysis. And you will see that here is very similar. The symplectic potential is E, the electric field is replaced by the metric, and the connection is replaced by, what else can it be? The Levi-Civita connection. Okay, so the structure is pretty much analogous. Of course, the key difference is that here this is a fundamental variable, here this is not. It has to be a function of the metric, and therefore you can re-express this in terms of two inverse matrices, and then a structure like this. The fact that the structure is like this, or sorry, maybe without going into too many details, I could just write like this. The fact that the structure is like this is already suggestive that we're going into a more Neumann-like variational problem, because we have variations of the derivatives as opposed to variations of the field themselves. And this can be made precise if we actually do the procedure of taking the pullback of this on a manifold. This is this derivative here. This is covariant. This is covariant because I put the delta there. Oh, no, sorry, you're right. Yes, sorry. I put it like this. Sorry. Yeah, maybe, I don't know. I'm kind of like rushing because of the time, but maybe it's worth it I give you the right formula. Just give me a second. Do I have the right? So, rho sigma, amazingly, the indices were right. I can even give a 1 over 8 pi here for free. And then that one was actually right. So 1 over 8 pi g mu rho g nu sigma nu delta g sigma. Okay. Yeah, you know, this just comes from when you take it, if you're doing linearized gravity, you know that the first order in the linearized field H, this looks like background -1 and then derivatives of H. And so that think of this as the H. Okay. So now, in the case of the scalar field, when I made that sanity check, I was very fast because we all know that phi dot is pi, the conjugate momentum. In gravity, the notion of conjugate momentum is a little bit more sophisticated because one has to use the tools of extrinsic geometry and embedding of hypersurfaces, which I'm assuming you are a little bit at least familiar with. And then if the boundary is space-like or time-like, so non-null boundary, one gets that the pullback of this theta can be written basically in this form, q delta pi d3x, where I'm not going to put the indices because I will have to read them. Okay, the indices are obviously just a, b, or mu, nu, mu, nu. It's just that the sign depends on which one you put up and down. So that's why I'm not writing them. Where q is the induced metric. K is the extrinsic geometry. And pi is, so pi mu nu is k mu nu minus q mu nu k. This is the ADM momentum. So sanity check, we get the ADM formulation of GR. And tilde, as usual, just means a square root of q in this case. This is the boundary term. The extrinsic geometry of the boundary. The ADM formalism, yes. So no. Okay, I'm sorry. You're thinking already about the momentum. Okay, fair enough. So what do you want me to call this? Canonical, so conjugated momentum? Don't call it, okay, conjugate. Because rightly, you're already thinking about the ADM momentum as in the generator of the Poincare symmetry at spatial infinity. Fair enough. This is the conjugate momentum that one gets when one does the ADM 3+1 splitting. So 3+1 conjugate momentum. Okay, very good. Okay. So you see that we get it naturally. So the variational principle for GR, for Einstein-Hilbert Lagrangian, is Neumann form. Now, to put it into Dirichlet form, you can observe that there are some identities that allow you to rewrite these as basically P delta Q. You see, I can do a change of polarization. So I can write these as total delta of Q pi minus pi delta Q, okay, and everything in D3x. See, I've just done a change of polarization like I would do there. And what is this delta? Well, you do the calculation, and this is 2k, square root of q. So if you add this boundary Lagrangian, you switch from Neumann to Dirichlet. This boundary Lagrangian is called Gibbons-Hawking-York boundary Lagrangian. You can do also something even more interesting, which is to have a mixed, so this would be Dirichlet. You can do something more interesting, which is to have a mixed variational principle, and this is called the conformal York. And in this case, what you hold fixed is the equivalence class under conformal transformations of the metric. so conformal class, and the trace of the extrinsic curvature. So it's like you have done a change of polarization, but only in one of the 6 components. The trace and volume you have traded for one another. And funnily enough, you can do this with the same, almost the same boundary term, it's just the numerical factor that is different. So this is a York boundary Lagrangian. So you have different different boundary conditions that give a well-defined variational principle, and that you can use to make your system. Now, if you think of this projection of this pullback on space, then you would think of this as this momenta. But if you think of this pullback on the time-like boundary, the formulas are the same, absolutely the same. And then you can think of this as different ideas on how to get conservative boundary conditions. Because you see that if you give boundary conditions which are delta pi equals 0, or delta q equals 0, or these mixed ones, then theta is 0, and therefore also omega would be 0 with conservative boundary conditions of any of these 3 types at the lateral boundary. Okay? So this is how the variational principle ties in with boundary conditions. Now, I guess there is another layer that one can discuss, which is the fact that because we have one boundary here, we have another boundary there, in gravity, we can always assume by choice of coordinates that this corner here is a perpendicular corner, and then that's enough. But in general, you might be interested in situations in which you allow this corner to be non-orthogonal. If the corner is non-orthogonal, then you need in the variational principle additional corner terms in the boundary Lagrangian, which I think this is what you were alluring to. So full variational principle may also require codimension 2 corner terms. These I will show you that play a less relevant role, at least insofar as the standard construction of charges and fluxes is understood. And maybe the last 5 minutes, because then I would like to let you go. You can do, now, for us, it's also interesting to do this gravitational pullback in the case of a null boundary, because that, as I was saying, allows us to identify this constraint-free data. The main difference, though, is that all these structures, you can get them by basically introducing just one additional structure on top of already the dynamics of the theory, which is a normal that describes where the boundary is. So let's say these are our background structures. A scalar field whose value equals 0 tells us where the boundary is, and then a choice of normal for the boundary, or f, I don't know. Now, in order to formulate things as usual, you choose the normalization of the normal so that this is plus or minus 1. The case of interest, that is a time-like boundary, so it's plus 1. But if you were to do it in the standard 3 plus 1 formalism, you would choose minus 1. And that's very important because that gives you a description of the boundary which is independent of the way you embed the boundary. So that means that you have introduced some backgrounds, but things will remain covariant. In the null case, so null boundary, there is no preferred normalization. In fact, the normal itself, so let me call it L. So we can, again, say that phi equals 0 is where the null boundary is. So let's say that n is located at phi equals 0. However, in order for it to be null, what we need is that the one form d phi has 0 norm. So if you choose phi as a coordinate itself, which we can always do, let's say, locally, then this is equivalent to say that g phi phi is equal to 0 at the hypersurface. And therefore, this is somehow, if you want, a gauge fixing, because you see, at least in these adapted coordinates, we have one component of the metric that is 0. But you don't have to choose adapted coordinates. What is important is that the this one form, then, which is the normal to the hypersurface, as zero norm. So let me now call the normal, again, L, to distinguish it from the null case. And then this will be the gradient of phi. And now I have no way of choosing f in any canonical way, because by this property, L mu is 0, okay? Where L mu is the vector defined by the metric acting on the normal. So that means that, first of all, there is no canonical normalization, because I can multiply by anything, this would still be 0. And now there's a little cascade of consequences of this. The first is that you see the vector L mu is actually tangent to the hypersurface. Because the definition of a tangent vector is that the scalar product to the one form, normal to the hypersurface, is 0. So the vector vanishes itself. So on these hypersurfaces, we have the normal, and so then the normal vector would point like this, and the tangent vectors are like that. But on a null surface, we have the normal, and the normal vector points along the null hypersurface. Okay, so it's tangent to it. Now, that's the first consequences. The second consequence, so tangent, so L mu tangent to n. Second important consequence is that the induced metric is degenerate. And this is intuitive because, on this null hypersurface, one of the possible directions has to be a direction of zero geometry because it's the direction along which light propagates. So it's quite intuitive that the induced metric will have like a 0 plus plus signature. And in fact, it has 0 plus plus signature where L is because it's tangent. If you don't want to make confusion between the indices, let's say I used hypersurface indices little a, just 1, 2, 3. So because it's tangent, L mu has only components 1, 2, 3. And so this is the null vector of the induced metric. And because the induced metric is degenerate, there is no projector, and it's a projector that we use to define K. There is no projector, no induced Levi-Civita connection. However, there's still geometry that you can do. First of all, it's true that there is no projector, but you can still define the Weingarten map. So you can just define the pullback of the ambient connection acting on this normal vector. This is called the Weingarten map. When you do this on the time-like or space-like slice, this gives you the extrinsic curvature. Here it does not, but I'll tell you in a second, very quickly, what it gives you. And for the connection, something that is not relevant for the following, but I thought it would be useful to say it because it makes connection with later classes. The problem of a null hypersurface is that the pullback of ambient connection is not a 3D connection, because what it does is that it takes tangent vectors to the hypersurface, and when you parallel transport them, they're no longer tangent. The obstruction that makes them no longer tangent, so L mu, X mu, X nu, number mu, Y mu, where X and Y are tangent, is proportional to the shear and expansion of the null hypersurface. What are the shear and the expansion? If you are familiar with null geodesic congruencies, like you take Wald's book, you can introduce the deformation tensor, and this will be given by a symmetric part, that's the shear, an antisymmetric part, that's 0, because we are hypersurface orthogonal, and the trace part, which is the expansion. And what is gamma in this description is that even though we have no projector on the 3D manifold, what we can do is that we can pick another null vector that is transverse to this one. And if you are familiar with the Newman-Penrose language, you will call this second vector n. So we have this pair of null vectors, and this null vector provides what is called a rigging of the null hypersurface. And then the subspace orthogonal to both L and N, it's this plus plus codimension 2 space-like cut. So this guy is a 2 by 2 induced metric. That guy has a projector, which I'm calling gamma. I don't remember what Wold calls it in his book, but anyway, this is this 2 plus 2 projector here. And then you see that there is no connection in general unless the hypersurface is shear-free and expansion-free. So only, and with some abuse of language, I'm going to call these non-expanding horizons. Non-expanding horizons, canonical connection. And scry is an example of non-expanding horizon in a certain description, and that's why one can have a connection description. But more in general, you don't get a connection description by just taking the pullback, but what you can do is that you can use this rigging vector to define, so in general, you can use the rigging to give you a one family of connections, one for each choice of rigging. And these are called the Carolian connections. And this is what Yannick will be talking about. Now, in this formalism, the shear is defined as the Lie derivative of the induced metric, which is degenerate, and the expansion is the Lie derivative of, if you want, the square root of the determinant of the 2 by 2 part, so to speak. And then you can do the same pullback once you've introduced these tools. And last thing that I say, promised. And now the pullback on this null hypersurface, you get something that instead of having this ADM type structure, where did it go? I don't know. I canceled it. Now it has a structure that is like sigma delta gamma plus pi mu delta L plus, I don't remember what I call this, maybe mu delta square root of Q, the determinant of the 2 by 2 part on the induced, or of the induced metric. And so the decomposition is richer, if you want, than the standard ADM in which we had just induced metric and momenta. Now we have an appearance of 3 different pairs, but what matters the most is this pair here. These are the constraint-free data, in which the shear is canonically conjugated to gamma. And therefore, again, you can give a characterization of conservative and dissipative boundary conditions. Conservative boundary conditions of Dirichlet type, you will require that the induced metric is held fixed, that this choice of normal is being held fixed, and in holding this fixed automatically makes that fixed too. So this would be the equivalent of our conservative boundary conditions. And the dissipative boundary conditions in this case are easier to describe because we can fix that the geometry is like this, so the only waves can be outgoing, and therefore, if we relax these, we know that we are allowing for gravitational waves to go through. What is tricky and has to be handled with care is how we still impose some boundary conditions, even though we're leaky, which we need to take care of gauge dependence and making things independent of our background structures. So sorry for being late. Group A2L, please don't take too much time in moving from here to the canteen, and let's reconvey at 2.